Now we need to go ahead and take our derivative using the definition again, but here we're dealing with a root in the denominator. So you're still going to go ahead and take your limit, plug x plus h into your original function, then go minus what you get when you plug in your original function. Still all over 0. Or not over 0, over h. Now we need to simplify this. To simplify this, all we have to do is combine the top together. But to do that, you got to have a common denominator. Your common denominator just happens to be this whole root here times this whole root here. So you got to multiply the first fraction top and bottom by a root of an x plus 1. The second fraction needs the root of an x plus h plus 1 top and bottom. Now we can go ahead and write the whole top as one fraction over our denominator, and what I'm saying for our denominator is just this right here. So we have our 1 times this root, and that's what we have for this first root, minus a 1 times our bigger root, and that's what we have here. Now you might be wondering what happened to that h that was on the bottom, and well, that's just right here. Remember, instead of dividing by h, that's multiplying by the reciprocal, which is 1 over h, which puts it on the bottom. Now, we need to continue to work with this. We need to somehow get the h out of the bottom so we can plug in a 0, because with that h still there, we'd have to be dividing by 0, and we can't do that. So we're going to take our original problem here in pink and multiply the top and bottom by the conjugate. And remember, the conjugate's the same thing, just with the sign in between switch. So it was a minus, it went to a plus. And you may have to pause the video as you're working this out. Then we FOIL the top. Your first terms, a root times a root, same thing, so they drop out. Remember, your outer terms and your inner terms when you're dealing with conjugates always drop. Then it's a negative times a positive, so that's why we have a negative here. And then this root times itself again, so that drops out. Then we just have the whole bottom. So we had what we have here in pink. Then it's got to be multiplied by what we had up there in black. Now here we can eliminate the parentheses on the top by distributing through the negative. You'll notice then that you can combine like terms. The x's drop, the 1's drop. So it really leaves you with, because these things drop, leaves you just with a negative h on the top. That negative h on top drops with the h in the bottom then. And so we get just a negative 1 on top. And so that's how we get that negative 1. Now that we no longer have that h in the bottom corner here, we can actually go ahead and plug in 0 for h. So replace all your h's with zeros, and you get this. You get this root times this root. And by the way, once you plug in h being 0, you no longer have to write your limit. This root times this root is just an x plus 1. Then you're going ahead and you're adding two roots together. A root plus a root, same root, gives you 2 of them, so that's why we have this 2. And it'd just be 2 of those roots, so that's why we have this. So this is your derivative. So here we have the graph of our original function in blue, which is the cube root of x. We also have graphed over there our derivative of the cube root of x, which is 1 over 2, or x to the 2/3. Now, as you look over here, you'll notice that, yes, you can draw your blue function without ever lifting up your pencil, so the blue function is continuous. However, the red one here has a vertical asymptote. That's because when you look at your derivative, which is right here, your denominator has a variable in it. And whenever that denominator is 0, it's going to have a vertical asymptote. So that's why we have a vertical asymptote at x being 0. So if your function is continuous, which it is, does that also imply that your derivative is continuous? Obviously not, since we have a vertical asymptote. So here we have a graph of our function. Is it going to be continuous for your derivative? Well, it has a sharp point in your curve, which you should remember is a cusp. You should remember from your definition of a cusp, that's a sharp point in your curve in which your derivative is discontinuous, which means your derivative does not exist there. So we would say no, since there's a cusp, because you have a slope of your tangent line at x equals 0. You really have a tangent line that could be horizontal, could be diagonal, either way, diagonal. So it really just kind of pivots all the way around there. There isn't one set tangent line. Your derivative, if you're looking at the one side, goes off towards positive infinity because it goes up faster and faster here. The slope of your tangent line is positive infinity. But once you get to the other side of 0, the slope of your tangent line is a big negative, so it's negative infinity. And there is no slope right at 0. So your derivative does not exist, because remember, your derivative is a two-sided limit. And your limit for your derivative, the slopes of your tangent lines, on the left side goes to positive infinity, on the right side goes to negative infinity. So your derivative does not represent or equal the same thing on each side. So, if a function is differentiable, is the original function continuous? Yes. If a function is differentiable, then it is continuous at C. So differentiability implies continuity. So if a function is differentiable at a particular point, then it is continuous. So this is a second way, instead of going through all three tests of continuity, to be able to show that a function is continuous at a particular point. However, because it is possible for a function to be continuous, like the last two examples, but not differentiable at a particular point, we would then say, well, continuity does not imply differentiability. Just because your function is continuous does not mean it's going to be differentiable at each and every point.